I think it should be standard practice for teachers too. But not all of them know what they're doing. So here we go. Kinetic energy and the work energy theorem. This is a nice way of, well, hold on. We'll get to the kinetic energy part. So a little bit of review of grade 11, I hope, is that kinetic energy is just the energy of an object has because of its motion. And so, again, we're not, science people are really boring at labeling things. Kinetic energy, we have E for energy, K for kinetic. And what it is equal to, the formula is we have 1/2, M is our mass, and V is our velocity squared. And that's how much energy you have. Timesing by 1/2 is the same thing as dividing by 2. So they're the same formula there. Hopefully you've seen that formula before. Now, what the work energy theorem essentially is all about is the fact that if you do some work on an object, pushing it, you're going to make it faster. I think that's pretty obvious. Hopefully you've experienced that in your life. All right. So we apply a force. It has we apply a force to a mass. It has initial velocity. Obviously, when you push something, you're going to make it go faster, as long as you're pushing it in the direction that it is moving. All right. Because that would be positive work. And so again, the total work, so this is the science explanation of that, is that the total work done on an object equals the change in the object's kinetic energy, provided there is no change in any form of energy. So we're looking at an isolated system, is what I would call it. And so essentially, to find the amount of change in energy, you need to look at the change in the speed, which was result in a change in kinetic energy. Because the one thing that doesn't change, of course, is the mass as you're being moved. All right, so we have delta E, the work put in, change in kinetic energy, again, is the result in there being a change in velocity. All right, so there's our formula right there that we're going to use. All right, so now we get to a couple of questions. So a whale with a mass of 1,500 kilograms is swimming with a speed of 6.1 meters per second. A large ship passes the whale, and its wake increases the whale's speed to 12.8 meters per second. Calculate the work done by the water on the whale. All right, so here we go. So again, we are looking for work, the energy, which in this case, going to use my formula here, results in a change of kinetic energy. All right, and again, when you have a change of kinetic energy, that means you have a change in speed. So what we're going to look at is 1/2, and this formula can look at different ways too, by the way, but I stick with this. It's the easiest to calculate, where I have 1/2 mv squared, mvf squared, our final velocity, minus 1/2 mvi squared. All right, so again, we're looking for work. All right, so again, I look at my values here. 6.1, that's what the whale started off moving at. VF here is what the final speed is, 12.8 meters per second. And of course, we have our mass here, which is 1,500 kilograms. All right, so again, as I've said many times, I got a half here, right? Well, I don't like a half. I always like to have numbers, so I'm going to change that fraction to a decimal. So here we go. So I got my 0.5. 0.5, there we go, times my mass, which is a 1,500. All right, VF squared. So again, my VF is 12.8, and I'm squaring that, so we'll do that. Subtract the initial kinetic energy, which again is going to be 0.5, times our mass, which is 1,500. And again, our VI squared. What's VI again? 6.1. All right, square. There we go. All right, so again, we are finding our work. So I got my W equals. The only thing here is you got to follow Bedmith. So I'm going to do this all at once. We're in grade 12U here. So let's see here. I go 12.8 squared. Oops, 12.8 squared. Got to do the Bedmith first. All right, then I times it by the mass. And then times it by my 0.5. And I get, oh, really, a round number? I'm just reading off the calculator here. 1228800. It's a cool number. All right, and so that's really 1,228,800. And I'm going to subtract. All right, let's see, back to the calculator again, following Bedmith's. I do 6.1 squared times my 1500 times 0.5. Decimal again, or not a decimal again. All right, so I get 279075. What's that actually as a number? 279,075. All right, so then I'm going to subtract those two numbers, and I'm going to get my answer. Notice how my answer is positive, right? Because this thing is being, the energy, the kinetic energy is being increased. And it's going to be increased with the amount of energy that's going to be, let's see here, subtract the two, I get 949,000 joules and 725. And again, joules. And again, as I said, work is positive because we're increasing the kinetic energy of this whale, or I should say the water is. All right, so there's an example number one. So again, put work in, you make things speed up, or the water put work in. All right, next one up. Police car, 2,400 kilograms, receives an emergency call, and so the driver increases the speed of the car to 33 meters per second. This increase in speed results in 310,000 joules of work being done on the car. Determine the police car's initial speed. All right, so again, I'm going to use my work formula. All right, the amount of work here. Again, we have a change in kinetic energy, so I'm going to look at 1/2. My mass is not changing. We have VF squared. Same thing over here where I have 1/2 MVI squared. Okay, so the information we have, let's see here. There's our mass, 2,400 kilograms. Now it increases the speed of the car to 33 meters per second. So that is our VF in this situation. And this is how much work we put in, or there is a change in kinetic energy. It's positive, so we're speeding up this car. This car is being sped up. All right, so that's our change in kinetic energy. Here's our work. All right, so again, I'm going to substitute in my values here. So let's see here. I got the amount of work. It's 310,000 joules equals, again, here's my 0.5. The mass of this car, we got 2,400. All right, and my VF, again, we have 33 squared. All right, now get to the initial kinetic energy. Again, so I'm going to go 0.5. The mass is 2,400. And, we were looking for VI. So we got VI. Let's go with capital V here. There we go. VI squared. All right. So let's see. What can I simplify here? Well, I can put some numbers together. And that's why I always do substitution, Ray. You and I talked about this instead of rearranging this formula, because I can put my numbers together because I got, let's see here. Again, doing bedmas, so I got to go 33 squared times the 2,400, then times 0.5. And let's see here. I end up with 13068. How many zeros here? 2 zeros. Okay. So what number is that? We have that 1,306,800. Okay. And well, I don't know VI squared, but I can do half of 2,400. I already know that's going to be 1,200 then. Whoops, 1,200. And again, we have our variable we're trying to find here, VI. Can't forget that it's squared. All right, so again, solving for VI. So I'm going to move this 1,306,000 over to the other side. All right, and so let's see here. I subtract those two. I'm going to get a negative number here clearly because I got 310. I'll write it out. 310,000 minus my 1,306,800 equals, can't forget my sign there, there's a negative 1,200 VI squared. All right, again, 310,000, subtract that number, one big one. So let's see, that's going to be definitely negative, but that's okay. 310,000, make sure I got the right zeros, minus 1,306,800. I get negative 996,800. All right, and again, that's going to equal my minus 1,200 VI squared. All right, so not last step. Watch what you're saying here. All right, so I still have to divide by my numerical coefficient. So I'm going to divide by negative 1200 on both sides. All right, and so I end up with a positive. Negative divided by negative, I get 830. Again, go to 2 decimal places because it goes 6666666, so it's going to be 67. Equals my VI squared. All right, now the final step for this, I take the square root of both sides, and my VI, my speed here is to 2 decimal places. It started off, and good thing is it is a lower number, which it has to be, 28.82 meters per second. And again, if you ever want to convert something, meters per second, to kilometers per hour, you times by 3.6. So in fact, this would be a velocity or speed, sorry, of 3.6, 103. That's pretty realistic. 0.75 kilometers per hour. And let's see, what do they end up with? 33 meters per second. That, in terms of kilometers per hour, is, again, times by 3.6. 118. So the police officer, 118.8 kilometers per hour. So the police officer didn't speed up that much, but they did. All right. Next one up. Here we go. An archer pulls back her bowstring loaded with a 22-gram arrow, then releases the string. If the arrow leaves the bowstring at a speed of 220 kilometers per hour, calculate the work on the arrow by the bowstring. All right. So here we go. So what do we got here? We have mass. We have leaves the bowstring at 220 kilometers an hour. That would be our VF. All right. 220 kilometers per hour. All right, and we want to know the work done on the arrow. So let's see here. What else do we know? Mass is 22 grams. All right. Oh, here's a secret value. Always a little physics interpretation. The initial velocity. Well, I hope if you're an archer, your initial velocity would be 0. All right. Okay, so what do we got here? Mass. Now, we have some issues here. We want the work, by the way. I better throw that in here. And so, surprise, surprise, we're going to use our formula where we have work is equal to, again, 1/2 mVF squared minus 1/2 mVI squared. Now, a couple of things here. We don't have standard units. In fact, we're messed up on both the VF and the M. Because we don't use kilometers per hour, but just like in my last example, when I went from meters per second to kilometers per hour, I times by 3.6. Well, when you're going the other way, you divide by 3.6. So 220 kilometers per hour, 220 divided by 3.6 is going to be 61.11 meters per second. All right, so there. Now I got that in standard units, but again, mass is in grams. I need it into kilograms. All right. So there is 1,000 grams in a kilogram. So I'm going to take my 22 and divide it by 1,000 to get it into kilograms. So I get move the decimal 3 spots, 0.022 kilograms. All right. Now that I've got everything in the right units here, now I can substitute in. All right. So let's see here. So I go, work is equal to, again, 0.5 for my half. My mass, very small here, 0.022. Whoops, 22. VF squared, put that in here. We have 61.11 squared. Now, here's something. My VI here is 0. So when I put a 0 in for my VI, that's terrible. It's a terrible 0. There we go. Put a 0 in there. 0 squared is 0. it doesn't matter what anything else is, because mass times 0 is 0, 1/2 times 0 is 0. This whole term here is 0. Because the arrow was initially at rest, it had no kinetic energy. So all the work is into making it move. So we didn't have an initial velocity. All right, so now I can just find my work, again, following Bedmus here, 61.11 squared, then times 0.022 times 0.5, I end up with 41.08 joules, which is kind of a small number, but the thing is that this is a small object, so it doesn't take as much energy to speed it up. Whereas if you have a much larger mass, it does take a lot more energy to speed it up the same amount. And then part B. What is the magnitude of the force of the bowstring that it exerts? Hold on. What is the magnitude of the force the bowstring exerts on the arrow if the force is applied over 10 centimeters? Okay, so we're looking for the magnitude of the force, the magnitude. So we're looking for F. All right, we know how much work was put in by the bowstring. It was 41.08 joules. All right, and our distance happens to vary in a small amount of time, or small area, or distance, I guess I should say. 10 centimeters, again, that is not in our standard units. There's 100 centimeters in a meter, so I'm going to divide by 100, and so I'm going to get 0.1 meters. All right, now this comes back to our formula that we used this afternoon, or this morning, where we have work is equal to F times D. All right, I'm going to substitute in here, so I have my 41.08 joules is equal to F times my 0.1. All right, and so now all I'm doing is dividing by my numerical coefficient here, 0.1 on both sides. And so my force is equal to, I'm just moving the decimal place over, so 410.8, and again, because we're all in our standard units here, newtons. And that's how much force that string applied to our arrow. All right, so that, folks,